Intellectual progress operates on a strict tension. We must generate novel ideas, but without the constraint of observable reality, they become entirely useless. The history of science does not move in a smooth, upward line. It oscillates between periods of rapid, explosive creativity and long stretches of careful, rigorous consolidation. We model this using three variables. First is C, the rate of claim production, showing how fast new hypotheses generate. Second is V, verification, the mechanism that empirically tests them. Finally, I is integration, where surviving claims settle into a stable lattice of established knowledge. For any scientific discipline to function effectively, it has to maintain an active homeostatic balance between all three of these rates. To track the stability of an epistemological system, we can look at this dial, which monitors a simple ratio, R, the claim production rate divided by the verification rate. If the verification rate vastly exceeds the generation of new claims, the system enters a conservative state. In this environment, innovation slows to a crawl, existing models calcify, and the discipline becomes hostile to unexpected discoveries because the barrier to entry is too high. The opposite failure state is far more dangerous. When claim generation outpaces verification, the system becomes uncoupled. Speculative theories multiply without constraint. Ideological fragmentation increases, and the signal-to-noise ratio drops so low that navigating the discipline becomes nearly impossible. Without empirical anchors to filter the output, there is no reliable way to distinguish a brilliant hypothesis from pure pseudoscience or speculative dogma. Runaway claim production creates a crisis of fragmentation. To survive, the system requires a regulatory constraint to pull it back to reality. Historically, the philosophical solution to this exact crisis of intellectual fragmentation was classical pragmatism. Thinkers like Charles Sanders Peirce, John Dewey, and William James developed pragmatism to manage the explosion of new ideas in the 19th and 20th centuries. Pragmatism rejects the idea that a hypothesis should be evaluated merely on its logical elegance or its internal consistency. Instead, it applies a strict filter. Does it work? Does it reliably predict outcomes? Does it improve our physical interaction with reality? In our dynamic rate, pragmatism functions as this homeostatic feedback loop. It prevents knowledge from drifting into pure speculation without crushing the imagination required to generate new claims in the first place. By forcing an ongoing, corrective interaction with the physical world, pragmatism stabilizes the evolution of knowledge and keeps it on track. But there is a critical exception to this model. An abundance of rapidly generated claims isn't always inherently destructive. While independent claims typically fragment, as we see in this diverging map, we have to account for the principle of organizational convergence of claims. This principle requires one specific condition. The competing hypotheses must remain strictly coupled to a single, shared, unresolved problem. When tethered to that common core, the behavior of the claims changes entirely. They stop diverging. Instead, they begin interacting, criticizing, and constraining one another. This localized friction generates intellectual turbulence. It operates exactly like turbulence in fluid dynamics. What initially appears as complete chaos eventually spawns highly structured, coherent vortices. We see this pattern clearly during the birth of evolutionary biology, or the early decades of quantum mechanics. At the time, those fields appeared to be a chaotic mess of contradictory claims. Yet, over decades, they synthesized into broad, stable conceptual continua. Under the right conditions, intellectual turbulence catalyzes the growth of structures far richer than any single hypothesis could achieve alone. We can scale this exact dynamic down from the macroscopic history of science to the microscopic operations of a single human brain. According to the Brain Kinematics Model, human cognition relies on simultaneously active competing hypotheses, known as strain packages. During waking hours, our external reality provides high empirical constraint. The verification rate stays dominant. But as the schematic shows, REM sleep flips the dynamic. It creates a high-generation, low-verification environment, where claim production vastly exceeds verification. Dreaming acts as an organizational sandbox. Fragmented claims can freely interact, conflict, and self-organize without any waking consequences. This creates a complete cognitive pipeline. Waking experience provides raw data, which leads to dream organization, which then provides new structures for the waking mind to evaluate. Once awake, that renewed organization is immediately subjected to critical reflection and experimental correction. Dreams generate novel conceptual networks, mimicking the self-organization seen in large-scale scientific development. Looking at these two systems side by side reveals how the macroscopic history of science and the nightly cognitive cycles of a single brain share a parallel cycle of divergence, constraint, and reorganization. Human knowledge cannot advance purely through unrestricted, runaway speculation. It also cannot advance through rigid conservatism and an over-reliance on immediate verification. This model forces us to redefine the dual role of reality in the evolution of knowledge. First, reality acts as a homeostatic constraint, providing continuous empirical correction. Second, it acts as a gravitational center, forcing competing ideas to interact around unresolved problems. This forced interaction drives the self-organization of increasingly comprehensive explanatory continua. A scientific or philosophical system remains highly resilient by channeling this intellectual turbulence into more comprehensive levels of organization.